In this video, we present our work titled, A Real-Time Affordable Predictive Trajectory Tracking Controller for Differential Drive Robots via Imitation Learning. Nonlinear Model Predictive Control, or NMPC, is a powerful approach for trajectory tracking of mobile robots, offering high accuracy and constraint handling. However, NMPC's heavy computation makes it difficult to deploy on resource-limited robots. Our goal is to design a data-driven trajectory tracking policy that achieves real-time performance with much lower computational cost. In this work, we adopt an imitation learning framework. Our expert is a nonlinear MPC controller with a prediction horizon of n equals 20, running in a physics-enabled simulation environment. The video on the right shows a sample demonstration of the expert policy executing its trajectory. We collect state action pairs from this controller and enrich the dataset by introducing state perturbations and expressing the system in terms of relative errors. Since the computation time of this expert exceeds the system sampling time, this limitation motivates our work on a learned policy for real-time execution. Secondly, we train a lightweight 1D convolutional network with residual blocks. A physics-aware loss informed by the robot's kinematics ensures the learned policy respects the underlying dynamics. The end result is a predictive tracking controller that runs in real time on embedded hardware. Here we demonstrate the trained policy tracking a lemniscate trajectory. For comparison, we also show an NMPC with prediction horizon 2, which is the maximum prediction horizon that can run on board. The black line indicates the reference trajectory, while the blue and red lines show the robot's actual paths under the trained policy and NMPC respectively. The learned policy not only tracks the reference closely while running entirely on board, but as the table highlights, its computation time remains well below the 60 Hz sampling limit. We also compare the controllers using the integral squared error. The trained policy achieves better tracking performance compared to the NMPC with low prediction horizon. This shows we can achieve accurate trajectory tracking without the heavy computation of traditional NMPC, allowing our controller to run in real time on robots with limited resources, making it more practical for real-world deployment. Next, we test the trained controller on different trajectories, starting with a simple circular path, and then moving to a more complex litigious curve. In both cases, the policy maintains accurate tracking while keeping low computational overhead. Importantly, it generalizes beyond the training scenarios, handling new and more challenging paths while maintaining predictive, stable motion. In summary, the proposed learning-based controller provides accurate and stable trajectory tracking for differential drive robots while significantly reducing computational cost. By imitating an expert NMPC policy, leveraging physics-aware learning, it generalizes effectively to new and unseen trajectories, offering a practical and efficient alternative to traditional model predictive control.